Welcome all. I'm Alan Roy with the session number 21BCE5368. First of all, thanks to Professor Abdul Qadir for giving me an opportunity to explore the NAND project. So in this project, we'll first discuss the basics of the NAND-Tetris simulation, and then we go for the higher higher topics such as gates and finally the building of the computer. Well, it's the building of the hack computer. Yeah. So first we discuss what is hack computer. A hack computer is basically a what the computer is developed in the status with its own RAM, CPU, and ROM, which are interconnected. And here we see how human thoughts are transformed into electronics and electrical engineering. So here we can see that human thought and written as a program in most probably in a high-level language, which is combined to form a virtual machine code, which is again translated and is again compared to a low-level code, which is with processor and assembler, and which is abstracted in the architecture. Which is again accessed in CPU, RAM, chipset, all processing is done there. And using gate logic, it converts to the process again. So here we can see that the upper half of the diagram of the design, it works with the software aspects, and the lower half works with the hardware aspects. Here we can see how chips are designed, and this is the example of an steel program. And the steel program is for XOR. In fact, this is how the steel program is. And you can see parts where the core of the program lies, where we define the gates, and all gates have in and input and output components. And here there are some Boolean operations which can be non-useful, like AND or not. So this AND, many of you may know, it's an analogy of the multiplication operation in mathematics, or it can be is analogous to addition operation. Not is a can be as negation, which many of you might have studied in mathematics. And here is an example for a Boolean function. A Boolean function can be defined as the collection of Boolean operations, or say collection of variables which are separated by Boolean operations, such as and, not, etc. Here are some Boolean entities. Here are the commutative laws, associative laws, distributive laws, and demogal laws, which are very important, which we use to solve many problems. Okay, and there's some points to note. So, any Boolean expression can be represented as by the use of NAND gates alone, so that they are not as Spinoza gates. You need not use a OR gate or AND gate or NOT gate, all other gates to form a big Boolean expression or to demonstrate a big Boolean function. You just in NAND gate. And also, Boolean function can also be represented with the help of AND NOT. Of course, you may know AND NOT together forms what NAND. So basically, and not presence of and not gates are more enough to represent any Boolean. So, as I mentioned, this is another typical analogy of AND gate and OR gate. AND gate is comparable with serial switches, and OR gates can be compared with parallel switches or parallel switches. Yeah, so here we can imagine there is no AND gate effect, so it's complicated. Yeah, here is what we have to earlier. This is AND gate. So if 0 can be assumed as a open connection, 1 can be assumed as a closed connection. So if one of them is 0, then the whole output is 0. That is, if one of the switches is off, then we don't get any output. That's not the case with OR gates. Only if both of them are 0 or both of them are off, that we don't getting out. Else we do. So that we can say like the AND gate is analogous to serial and the OR gate is analogous to parallel switches as we are learned in integration. So we are completing the main part of our lecture. So here you see what is STL. As you say, we have written HTL code for so HTL code is the specialized computer language. It's used to describe the behavior of electronic circuits, mostly digital logic circuits. So it gives a precise, it gives the developer or the user an idea of how an electronic circuit looks like, or how its computer interface works. It also allows the synthesis of HTL execution with netlist, and it's there are higher topics, of course. With mixed up. So here is the simulation process for this HTL file. So here we load the HTL file to hardware simulator. We enter the values zeros and ones as we enter here the zeros and ones, and we evaluate the system. We first this button, and we can see the values in here the expert pins, the internal pins as well as the expert output pins. Here we see the intermediate pins. What are the intermediate outputs, and here we see the finder. So this is how you have to do. Mostly you will have to add your file to the project 004. Otherwise, you may face the issues in running the program. You may face issues in finding or say the display of this eval button. Yeah. And now we want projects. So in project one, we build the gates like NOT, AND, or XOR. XOR max, maximum, italian. So we'll first start with the multiplexer. So multiplexer is a selective device, selects and outputs the possible of the two. Widely used leads to listening communication networks. And you see, as you can see, whenever the A is zero and select but select is zero, we get the output as zero. And whenever is one and select is one, we get the output as one. The demultiplexer is can be said as the multiplex inverse of the multiplexer. It distributes a single value to many possible destinations. There are many variations of that multiplexer, some to 16 to 4, 8 to 2, etc. And here we come to NAND gate. I will have a demonstration for the NAND gate. So we continue the session and this is the demonstration for the AND and it's for the NOT gate, and we can see whatever the input is, irrespective of whatever the input is, we get the inverse. And XOR gate can be expanded as like A and B plus, I mean, negation, I mean, not A and B plus A and not B. It mostly gives, when you give both are inputs as 0, you get output as 0, and both, if A is 0 and B is 1, you get the output as 1. And when, I mean, if the outputs are different, I mean, if the inputs are same, you get the output as 0, and and if the inputs are different, you get the output as one. Circuit, and this is called the demonstration for the Mux one, and here is the demonstration for Dmax. Next, moving on to this is the 16-bit AND operator, and see this is the input value. So this is what it as input, and this is the output. And by now 16 is the OR operation involving 16 bit numbers, and is the max 16-bit max operator, and also it is the 8-way OR operator and max 4-way with single max operator. Here we can see the Dmax 8-way, and this is how the output is the whatever values are getting in between is in there. Dmax 4-way kindly. Yes, and also. Thank you. Thank you.